Hello guys, back with another video and we're back to power electronics after a while. The last thing what I did was the Chook converter open loop, and yeah, the video was up maybe 1 or 1.5 month back, so it's been a while since that. So yeah, back with another DC-DC converter, and you can see here it's the buck converter. And of course we have done the buck in the past, but we did that with the TL494, the PWM IC, and it was fully analog or discrete, whatever you want to call it, and it was open loop. So basically, we were varying the duty with a pot, and yeah, we were able to see the entire range. But often, when we actually use buck converters, we want it to be at a fixed voltage, right? Like, let's say you have a 12-volt source and you want it to give you a constant 5 volts. That's a very common thing, 12 to 5 volts, and you want that 5 volts rail to be constant irrespective of whatever load you put there, of course within limits, but still, like let's say you have a light load and then suddenly you switch to a heavy load, it should be able to maintain the 5 volts, right? So that's where closed loop control comes in. And all this while we have been doing a lot of open loop control. So closed loop control is where power electronics basically meets control systems. So yeah, you have to sort of marry both of them, and yeah, the system will have to work together. And control system comes with its own quirks, tuning the controller. So that's a little bit of what I'm going to be showing today. And yeah, so the buck is there, and what we're going to be doing is we're going to be doing closed loop, and we're going to show the output and yeah, the circuit of course at the end. So before that, another second thing is, of course, you can implement closed loop control. What we're going to be doing today is a PI controller, which is proportional and integral. There's also derivative, and together they call it the PID control. But generally, for a power converter like this, a PI converter should be enough. We don't really need the derivative part, because derivative is basically for fast changes. It reacts to a sudden change, and as such there isn't a lot of sudden change here, so the derivative isn't needed. The proportional is basic, that is definitely required. It's proportional control, as it says in its name. It basically it decides how fast your response is, and it responds to the current error what is there at that point of time. So that's why proportional, so it's proportional to your current error. And second is the integral. You can see it's called integral because basically it's a summation of the error. And what this is required is because after a while the proportional, once there are no changes and it's at steady state, the proportional will basically do nothing. And but you won't reach your desired voltage, there will be an error, and that error is basically called the steady state error. To eliminate that, you need this integral term, which will over the time reduce this steady state error and help you get close to your set point, which is your desired voltage. So you need the I, and these are the two gains basically. They call them Kp and Ki, proportional gain, integral gain. And this is just a basic control block diagram. If this is currently in the time domain, so everything is in T. If you convert this to Laplace, everything will be in S. So let's say you have your input, which is R of t, and your output, which is desired, which is generally denoted with C of t. Here it's M, but whatever. And the difference with this is the feedback part. That's the whole point. The difference between what it actually is and your set point will give a error voltage. In this case, yeah, E of t, and that will go through your gain of Kp, which will directly be Kp into E since it's multiplied, and it will be Kp, and it will be Ki times the integral of the error. And this is for the steady state, this is for the current error, and both of these will get added and it will form your total gain, and that is applied to your actual buck converter, the entire transfer function of that. So currently our plant is basically the buck converter, and yeah, so if you tune these well enough, you should reach your set point. So of course you can implement this PI controller in discrete. They do it with op amps and stuff, all the capacitors, resistors and all, but it's a bit of work and it's a little cumbersome changing all those capacitors and all. So these days, of course, we all do digital control. It's much easier, and that's exactly what I'm going to be doing today. As usual, we're going to be using the MSP 430, the simple 16-bit microcontroller. It's great for simple things like this. So before I jump into the code, I'll just show you the schematic once. So this is the schematic. uh, First part is, this is the power converter, of course, the buck converter. We have the switch IRFZ441, the freewheeling diode 5819 Schottky, 1 millihenry and 100 microfarad is our LC filter on the output, and the load is going to be 100 ohm. We're going to be starting with that, and of course you have to drive this from PWM, from the driver, which I'll show in a bit, and 10 ohm gating resistor to eliminate ringing and all of that. And the driver, as I said, is we need a high side, right? You can see it's the high side. We've discussed it before. This is not a low side switch, this is a high side switch, so you need a high side driver. So we're going to be using the IR2110, also used multiple times in the past. So you can give your high side input from your microcontroller, and you basically give it from HIN and VSS, which is your low voltage part from your microcontroller, and this is going to be the high current side, and it will be level shifted. Of course, microcontroller will give like 3.3 volt PWM, and it will be level shifted to 10 or 12 volts. Here I'm giving 10 volts, so that will be that. And yeah, this is the peripheral circuit. You need the bootstrap diode, the capacitor, and I haven't indicated here in the schematic, but you need the bypass capacitor and decoupling and all of that. So that is there, and basically this is going to be your high side output, and that goes here. So from here till here, that drives your gate. And yeah, with respect to gate and source, you have to give the floating ground here. That's only then will it drive the switch actually. And since we need feedback, right, as I said, we're going to be sensing the voltage, and our input voltage is what, 10 volts, right? And of course that's much too high for a microcontroller to directly sense. They'll just destroy it. Generally the ADC, which is an important part of what we're going to be doing, you can go check out the video which I did before this. It's on ADC. This is the basics of it. So for the analog to digital converter, we need to sample the voltage, right? So here we need to basically do a simple voltage divider. We divide the actual output voltage, and we can sense the safe part of it. So let's say we use a 33k and 10k like I did here. The voltage across this by the voltage divider rule is of course going to be according to the formula V into R2 by R1 plus R2, and it's going to be much lesser since this is going to have the majority of the voltage drop across the output. So you can make sure to choose your resistors in such a way that the output across this resistor comes within the range of the ADC. So something like 0 to 3.3 volt, and I'm going to be using the 2.5 volt reference in the MSP. I'm not going to be using 3.3. So 2.5, that's why I've designed it in such a way. And just a low pass filter. Sometimes they don't use this, but I've used it and it seems to be working fine. 1k and 100 nanofarad, it roughly gives like a 1.5 kilohertz cutoff just to eliminate the noise and all. So yeah, that's the low pass filter. And you'll be thinking, what diode is this? This diode is basically a clamping diode, and this is for over voltage protection, and that's pretty important in power converters like this. This is a buck converter, so as such you won't get a voltage greater than your input voltage. That's literally the point. It's a buck converter, it steps down voltage. But later if we do the boost, this will play a much more important role, because let's say something happens. Of course nothing should happen in normal cases, but let's say something happens and suddenly the voltage across this shoots up to let's say 8, 9 or 10 volts or even higher. We know the ADC can't handle more than 3.3 and somehow maybe 5 volts, right? It will basically just get fried and your entire board will go for a toss. So you need to protect that, and that's exactly why this clamping diode exists. And what that basically does is, somehow if the voltage across this gets above this point, right? So this point is where your voltage across this comes, this node. Somehow if it goes above 3.3 volts, and 3.3 volts is basically coming from the microcontroller that's available, you get 3.3 and 5. So somehow if this voltage goes higher than this, basically this will get forward biased, and the current is already low since this divider is there. So basically this error current will flow through this path till the rail of the microcontroller, and you can maybe detect this later and maybe stop the converter if some error is happening, but basically nothing will happen to your ADC. Over current protection is there because you have this resistor divider and the current is already low, and over voltage is there because you have this clamping diode. So both of these important things need to be handled generally when you are combining power electronics with control. On a microcontroller you need to have these two protections. So this will go to our ADC and we'll sense it from there, and it's basically a 10-bit ADC, right, the MSP430. So your voltage between 0 to 2.5 volts will basically get transformed to 0 to 1023, which is the 10-bit digital value. So yeah, that's basically the circuit. Now I'll go into the code. I won't go too into it, but yeah, this is the basic code. And first, just going into the main, we're just setting up the uh, PWM timer, and after that the timer interrupt for the ADC, and the ADC itself. So you do need to set up the ADC depending on whatever the reference and all of that. And the ADC itself, you need to sample it at a fixed time, right? That's how it's going to read the voltage. And here my switching frequency for the power converter is basically 50 kilohertz is what I've taken. So generally they take the sampling maybe 1/5 to 1/10 of this frequency. So I'm taking 1/5. So I'm going to be basically sampling at 5 kilohertz, and our switching is 50 kilohertz. So basically 10 cycles. So that is going to be our sampling timer. And later our PWM, where the actual output, this is going to decide the output voltage, right? If let's say your output voltage is low, you need to increase the duty. So it will basically change this register value, the capture compare register, and if the voltage is high, it's going to reduce it. So we have, that's what closed loop control is about. And if you don't get this ADC part, you can go watch the earlier video. As I said, I've explained it in more detail. And yeah, in the ADC itself, once the ADC reads the value, it's gonna come to this interrupt, and this is the ISR, the interrupt service routine. Here we're basically gonna be calculating the error voltage, which is our reference, which is, let's say, 5 volts right now. And after that it calculates the error, which is the actual measure, the reference minus the actual measurement. And for the integral part, it adds the errors, right, over time. So it's plus shorthand, plus equal to. Then this is important. This is something which is known as inductor, the integral wind up. So you need to clamp it, because over the time, let's say in the start, basically you have 0 volts on the output, right? So suddenly there'll be a very large error, and later, even though it gets fixed, this thing will still be a very large value, the integral part of it. So you basically need to clamp it and tell it like, you can't go above this is the maximum, and same thing for minimum. So yeah, this part is there. And after that, this is the actual calculation. As I said, if you see the plant, it's the error is basically Kp times E plus Ki times integral of E, right? So that's exactly what is going on here. Kp times your error plus Ki times the integral part of it. And this is a little bit of scaling. I won't go too much into detail, but you need to sort of scale this down. And another important thing is clamping the duty. Here it's a buck converter, so 100% duty would basically just get you your input voltage. Shouldn't be a problem, but I've just clamped it at 95 just for the sake of it, and minimum is of course 0. So yeah, 95% and 0%, and we're going to be writing this duty calculation. This is going to be the actual output, which is the duty cycle of the timer. It's going to decide that. And for the KPKI values is where most of the time goes. It took me a couple of 1 hour or so to just tune these values. This is pure control work, and yeah, sort of trial and error, a little bit of board plots and all of that. So yeah, KP is 150 for me and KI is 10. And yeah, just all of these variables for it, not too important. And yeah, that's the entire code for generating the reading the ADC and basically generating the PWM. So now that the code is out of the way and the circuit, let's go to the hardware. Okay guys, this is the hardware, and yeah, messy, a little bit messy, but not too many components this time. And big part is, since I made the the small PCB for the driver board, It's simplified a lot of the problems which I was facing before, so this is good. It has the screw terminals and all, and this is the IR2110. So yeah, this is the MSP430, the board, and we're sending the PWM over here, and this is the actual power converter. There's our MOSFET, our inductor, capacitor, and the 10 ohm resistor, and the load is here. I've just put it inside the breadboard. We could have used crocodile cables, but these leads are not too big, they should be fine. And this is a 100 ohm load, as I said. And we're gonna be viewing the output on the oscilloscope. Here we can see the duty, and we have a voltmeter set up to both of the things, so we can see the output voltage as well as what duty it's pushing. So yeah, basically the only thing left is I've flashed the code too, so the only thing left is to connect the power supply here. So I'll just do that. And yeah, I connected the power supply here, and you can see we have sort of 4.84 volts, and it's pushing about exactly 50% duty, which is good. And we're just a little bit off the actual desired 5 volts, just what 100 millivolt, which is shouldn't be too much of a worry. And that's probably because of all the breadboard stuff, but other than that, closed loop control seems to be working good. Our gains look fine. And another way to demonstrate this is basically, let's say you add a heavier load, right? Currently, yeah, look, see, you can see now it's at 4.9. The steady state error is being rectified. So now we have, let's say I have another 22 ohm resistor in my hand, 33 ohm, sorry. So currently it's 100 ohm, right? If I make this in parallel with this, basically the current draw will increase, right? And if this output voltage is still maintained, then you can declare that your closed loop control works fine. So that's what I'm going to be doing now. We have this 33 ohm, right? So now I'll just put it in parallel with this. I'll just touch it here, and you can see the duty has sort of jumped up to 60% because it's drawing more current, right? So it has to push more voltage, and you can see our output voltage is now at 4.76, which is slightly dropped. It's sagged a little bit because of the heavier load. Our equivalent resistance is almost 22 ohm now, but roughly still, if you say your margin is, let's say 200 300 millivolt, we're still within that, so it's looking good. Our 5 volts is sort of being maintained, and maybe if you tune this ki part a little bit better, you might even get a better response, but this seems good to me for now. And yeah, so that was the 5 volt part. And now if I remove this load, you can see it's gone back to 50% duty cycle, and we're back to 4.93 volts. So yeah, that's that. And just to show that not just 5 volts, you can set it to any value you want, which was basically here, right, in the vref. And this is basically 476 is basically just 5 volts if you apply all the ADC formulas and all that. So what I'm going to be doing now is, let's go for a higher voltage. Let's say you want 7 volts constant, so then your vref would basically change to 666. Just a calculation which I did on the calculator right now. So let's change this to 666. And now I'll just flash the new code with the changed value. Yeah, and I've flashed the 7 volt part, and you can see now the duty is around 71%. And on the output we are getting almost 6.93, which is so close to our desired, so it's practically perfect. Same 100 ohm load. And now we can try the same 100 ohm test. We can put it in parallel, and of course the current draw is going to increase even more since the voltage is much higher. But you can see now I've put this in parallel, and your duty has basically shot up to almost 89%, but your voltage is still maintained at 6.8 volts. And that's the beauty of closed loop control. Even though you have increased the load, the output voltage remains constant because it adjusts the duty. And if I just pull off this load, you can see immediately the controller adjusts the duty, and we're back to 70% and 7 volts. So that's the second voltage which we tried. And let's do a last third case. Let's say we want something like 3.3 volts, right? That's another famous voltage. So now to change that, again we have to change the reference here. So now the reference is basically going to be 314. So let's set that here. I'm going to change this to 314, and yeah, I'll flash the code. Yeah, I flashed the code again, and you can see now we're at a much lower duty. Since we want a much lower voltage, we're at 33% duty, and you can see our output voltage is 3.2 volts roughly, which is again within almost 100 millivolt of our desired, which is great with the same 100 ohm load. And for the final test, we can do the same, putting in parallel test and draw a little bit of more current. So I'll just put that in parallel. You can see the duty shot up to about 40%, and our output voltage again has sagged a bit. It has become around 3.1 volt, but yeah, this is where the tuning part of it comes. If you tune it better, you will get a better response. If I throw off the load again, yeah, we have about 3.2 volts, and our duty goes back to 33%. So yeah, that was the whole buck converter demonstration and closed loop. And this is probably going to be the start of like a closed loop series, which is the next level in power electronics, closed loop. So we got to get out of open loop now. So yeah, that was the whole demonstration. I think the video is probably a bit too long, 20 minutes, but since I had to cover the entire thing, it took a bit long. But I hope you learned a thing or two, and sort of got the maybe a little bit of motivation to do closed loop control, which is, of course, it's a very big step. It took me a bit of time to do it myself. So yeah, just to mention, I forgot to show it before. This is the voltage divider. We have the 33k and 10k there, and that's the low pass filter, 1k and 100 nanofarad. And yeah, this orange wire is basically how it's going back and reading it from the ADC. So yeah, that was the whole demonstration. I hope you learned a thing or two, and yeah, I did learn something. So yeah, thank you.